Thank you, Mike. As Mike said, I'm Ann Smith. I'm also with NERA Economic Consulting. I work with Scott Bloomberg. And I'm going to go into a different dimension of the question of the socioeconomic impacts of thinking about environmental regulations or regulations in general. So I'm going to talk about the potential economic impacts, and I'll explain how that's different from the compliance costs in just a second, and also distributional impacts of the NAAQS. I'll say also that, as Scott said, much of the work that I will be presenting that's not just general background about economic impact techniques was funded by the National Association of Manufacturers, and the results that you'll see for the state of Texas have been funded by TCEQ. So the issues I'm going to cover in my presentation are, first of all, what's the role and the need for what we call economic impact models, and what's the difference between the compliance cost estimates that we just saw in the prior presentation, uncertain or certain. They're certainly different than economic impact estimates, and I'll explain those differences, and methods that economists use to assess what the economic impacts are on a forward-looking basis for major regulations, and how that ties into the historical look back that we've seen from the empirical analysis that Dan Milliman went through in the first presentation. I'll go through some results for the 65 ppb Ozone NAAQS case and end with some discussion around the limitations and uncertainties. So as Professor Milliman presented, there are ways to look at historical evidence of economic impacts. And the key thing is that if you're trying to project the future impacts of new regulations that haven't yet been implemented, that can't be based on simple extrapolations from the findings of those historical impact studies. Rather, those studies really present sort of evidence to support a theoretical set of hypotheses about how the economy works. They do show that although it varies from type of impact to type of impact and sector to sector, that there are generally have been found net negative impacts from the regulatory spending that has occurred historically. But the thing to know before we go forward is that those studies, if you notice the dates on the data that were in them, they ended with data in around 1995. There are a couple using data that go as late as around 2000. So we're looking in those studies at spending that occurred many years ago in the 1970s through 1990s. And that was a period of time when the policies that were in play were less stringent than the ones we're looking at today, and forward-looking as well, and also affected a much narrower set of emitting sources. And as Professor Milliman said, they were pretty much focused on manufacturing sector in particular. Economic impact models that I'm going to be talking about are used to simulate the types of economic interactions that go with the theories that those empirical studies have more or less confirmed work or are at play when regulatory costs come into effect. But these models, because they're forward-looking, they take into account present and projected market outcomes rather than market outcomes or market situations from 15, 20, 30 years ago. They contain and are intended to represent the best available knowledge on current production processes and production relationships, that is, as well as to the extent that they have bottom-up features, sort of technological detail, they can incorporate projected new technologies and see if they will be taken up in the marketplace when regulatory pressures make them cost-effective. They also allow us to input specific estimates of each new regulation's projected incremental cost. So the terminology I want to clarify here is compliance cost versus economic impact. And I specifically clarify it's the economic impacts from compliance costs. So Mr. Bloomberg was speaking about compliance cost only. And examples of compliance costs are what are the expenditures that emitters must make to reduce their emissions? Those are dollar numbers. What is the government spending that may be needed to prepare SIPs or fund rebate programs to get older vehicles off the roads, for instance? Those are in dollars. Estimates of what households may have to spend including, well, I meant enhanced I&M costs, not O&M. So you see, we did at least refer to I&M at some point in our analysis. It's certainly on our minds what's happening. And then additionally, there are other types of constraints that can go into the models that maybe can't be analyzed or directly estimated as dollars, but instead a model will actually calculate. An example of that Scott referred to was the costs of what happens if you start to close down coal-fired power plants. In our model, that serves as a constraint in the model, which then calculates what those costs are endogenously in the model. Okay, so those are the costs. Those are the things that we consider costs. So most of them come with dollar numbers, but some of them can come as sort of operational constraints that you would apply to your economic forecast. But the economic impacts are things like changes in household spending power due to economic productivity changes, or the productivity changes themselves. Changes in economic activity, GDP, or gross domestic product, is often the most common one that's referred to for that, but there's also just change in value added in certain sectors. Changes in market shares, for instance, market shares of fuels. As you'll see, there's some pretty substantial market share shifts that can occur. These aren't macroeconomic in scale, but they certainly do have a big impact on macroeconomic forecasts, and or outcomes, I should say. And changes in employment are frequently a topic that people are interested in that come out of macroeconomic models, but frankly, I find are some of the least informative outputs from these types of models. And then there's the distributional impacts that can come from these models. They not only tell us something about the magnitude of the effect on the economy, but they can help us understand where in the economy you can expect to see these effects. What sectors, what regions, and depending on your model, how income levels are coming up with it. Economic impacts can be long-term in nature, or they can be transitional, short-term in nature. And those are two very different types of effects, and different types of models get at them. I'm not going to pretend that we've addressed all of them. I just want it to be clear that there are all these different types of economic impacts that have a temporal dimension as well. And now it's not advancing. So, next slide, please. There we go. No, now back. Okay, so I was just going to do a Henry Nickel game where I just say next slide and I keep talking, but it doesn't look like I'm going to have to do that right now. That does an anecdote from yesterday morning's presentation. If nobody else, if some of you didn't hear that. So the main thing I want to point out before I move forward is EPA's regulatory impact analysis, the RIA, contains cost estimates, compliance cost estimates, but in that regulatory impact analysis, there is no economic impact analysis. And it's economic impact analysis I'm going to turn to. So we can't refer to what did EPA do here. Okay, how are compliance cost estimates and economic impact estimates related? Well, so we've got one and the other, and in between the two lies what we call as economists a model, and particularly a macroeconomic model. A lot of other people might call this a black box, and I like to keep my slides from being too drab, so I made this box be blue. But the main point is they are related by filtering the cost estimates into the economic model, and out come the economic impacts depending on what kind of model you have and what features it has, what types of relationships it has. But what you can think of that model is it's a formulation, a mathematical formulation of those theoretical relationships that Professor Millamant was talking about, which he then had looked for evidence of or showed the evidence in the literature as to whether those theoretical relationships are in effect. In a model such as this, we assume they're in effect. So you have to make assumptions. We assume they're in effect. We use the most up-to-date parameters to identify the nature of those relationships, and then we use that to project forward-looking impacts. Compliance costs, I want to say another reason you use a model is compliance costs. You may know what sector bears them, but you don't know what sector actually, in the end, where the incidence of those impacts are. They can actually occur, the impacts from the compliance spending can actually occur in pretty far-flung locations from the sectors or the regions or even the people that face those costs and have to bear the direct spending. I'll just give a couple examples. And these are just intended to be just sort of intuitive and not the details of how the model works, but these sort of relationships exist in the models. For example, businesses that face higher costs because they have to comply with, say, an Ozone NAAQS, they might pass those costs through their customers. Electric utilities are a clear example of that. Usually they can pass it through if they're regulated into their rates. So they pass, whoever those business sectors are, if they're utilities or another type of business, they may pass those costs through to their customers. Those customers might be producers in other sectors of the economy. They might be households. To the extent it goes to other sectors who have to bear this higher cost of that product in their production process, they may be able to pass it through. But at some point, you run into certain businesses where the shareholder is going to bear some of that cost, and that in turn finds its way back to households. Capital spending to control emissions can divert capital budgets away from other productive investments. So there's a resource base of capital, and there's some limits on it. When it's spent in one dimension, that can limit how much gets spent in other dimensions. In turn, that lack of as much productive type of investment can reduce labor productivity, it can reduce other forms of productivity across the economy, and all of this can translate into reductions in workers' incomes. And just a third example, and these are by no means exhaustive, the rebate programs, for instance, to incentivize owners of relatively older vehicles to scrap them earlier than they would otherwise do so. And here we mean scrap them rather than sell them to get some other person who will then continue to use them. Well, that reduces other government services. The government has to find the money for those rebate programs, which in turn either reduces the services other types of services that people might otherwise have gotten from the government, or it might mean higher taxes. Again, all of this can translate back to the household and reduce consumption at the household level, or reduce spending power. However you want to put it, you may see a theme here that the incidents may lie in different places in different sectors of the economy, but ultimately, as these models project, it all comes back to what the consumer has in the way of standard of living, ability to consume. So by one way or another, economic models bring this kind of, all these impacts back to the consumer and the household budget. You'll see how some of that works. Now, the typical type of macro model that's needed to assess a really wide-ranging policy, such as the Ozone NAAQS, is called a computable general equilibrium model, or a CGE. Just think of it as it finds the equilibrium. Computable, it just means it computes it. And the important thing to know about a CGE model is that these models have to account for both the costs, the spending of the policy, but also the gains, in that anytime a dollar is spent, somebody is being hired or some equipment is being rented, there's economic activity that goes with those costs. And a CGE model makes sure that loop is closed. I guess if you want to say an analogy in scientific terms, is it forces a mass balance. It preserves mass across the economy, except to the extent that some of that mass may be thrown out if it's totally non-productive. But the point is, every expense to reduce emissions is also seen as an economic gain for the providers of those either technologies or fuels or services that have newly become demanded as a result of the regulation. And the increased spending on equipment or construction to reduce emissions is seen as an increase in both demand for labor and demand for capital, as well as being seen as a reduction in the overall productivity of the productive aspects of the economy. And so we end up with the net effect in a CGE, coming from a CGE model. But as I said already, what you do also learn from a CGE model is not just a net effect that's like a single number, is it up or down, but you get to see where in the economy did the costs end up pinching the most and who benefited the most. And the who, this isn't necessarily individuals, it's also sectors and regions. Now, CGE models, at least most of the ones that I know of, project a long-run equilibrium. And they don't really do a very good job at getting at transitional impacts, because transitional impacts are fundamentally not equilibrium phenomena. So what we get out of a model like this, if we're going to use just a CGE model, is some information on where the economy will settle in the long run after all the dust is settled. And usually the models assume that they get there sort of almost overnight, unless the developer puts in specific sort of lags in how fast transition can occur. So the important thing to know is that this might, in this sense, they might understate policy impacts, because transitional costs getting from one equilibrium to another can be fairly costly, and that is just not addressed. And the economic literature on employment impacts does suggest that when it comes to job transitions in workers, this can be a pretty substantial individualized effect. And we saw some of that, I think, to a certain extent in the presentation, the first presentation in this session. But the other things that are missing is that there's uncertainty in the economy, there's surprises, there's going to be volatility in prices, and sometimes regulations can actually create some volatility that wouldn't have otherwise been there. That can also affect the quality of business decision-making, may not exactly be perfect foresight and perfect decision-making and least cost outcomes. And that'll be missed as well by a CGE model. Now, I'm going to turn to examples of economic impact analyses for the Ozone NAAQS. I said examples. I looked around for examples, but I found only the one that we had developed, so I'm going to have to focus on that one. I really would have done a more broader literature review of other people's estimates if there were any, but I did a docket, what we call a docket dive. Went into the NAAQS docket and looked all around for other people's comments, trying to find any economic impact analyses, and I didn't find any, although there were some 340,000 sets of comments, so it was a little difficult to make sure I hit everything. But after I got through the first 50 pages of the website, I decided I wasn't likely to find more, particularly since nobody had ever mentioned any to me. We did an economic impact analysis at NERA. As Mr. Bloomberg mentioned, we did one in July of 2014 using older data that looked at the 60 ppb NAAQS. And then in February, not long after the EPA released all of its new data in a big tsunami of data files, we updated our analysis, and also because the proposal was now looking at a range only from 65 to 70, we decided to look at the 65 ppb to sort of look at the worst case. And now today, I'm going to be presenting also some economic impacts that TCEQ has funded us to do that build on this same analysis, but it looks in more detail, in more granular detail at the state of Texas and its economy and its reduction needs. So I'll be showing these side by side, and just be aware they're completely consistent with each other. I should also mention in my docket dive, I looked at the RIA, and EPA did not have an economic impact analysis in its RIA. So there's also not an EPA analysis. I said that before, but just wanted to repeat it. Here we are back to the box, but now I'm going to show you NERA's box in sort of Technicolor here. I needed to get some color into my slides. I've replaced that simple blue box from before with showing you a little more of the detail beneath the covers in our model, but I'm not going to try to take you through and justify every element of this model. It's been developed with a lot of effort. It's a full model of the entire U.S. economy. It's got linkages with trade. And it's got individual sectors, which is mostly what you see in the various colored boxes here. We have several non-energy sectors, about agriculture, industry, energy-intensive industry, motor vehicle manufacturing, other manufacturing, trucking, commercial trucking that is, other forms of commercial transportation, such as airlines and railroads, and then other commercial and service entities, all broken out separately. On the energy sector side, over on the right-hand side, we have the electricity sector in very great detail, as well as the coal sector and natural gas, crude oil, and other forms of fuels that can supply energy needs of the sectors, as well as of the households. And we have government in there. We have taxes represented. But I'm not going to go into all this detail. The main thing I want to mention is that on the electric sector, we've mentioned that we've assumed certain coal-fired power plants would be closed, or that their emissions would be reduced very deeply in some other states as a result of the need to get the NOx emissions down from the electric sector, since that's a most obvious target, if you noticed from the bar charts of where the emissions will be that need to be cut further to get to the deep reductions that are needed for 65 ppb NAAQS. Now, our model has a full unit-level representation of the entire U.S. electricity generating sector in its individual markets, Texas being one of those markets. And our model actually endogenously determines, when we say those emissions have to come down, what will be the least cost replacement for those sources of electricity. So the lights don't go out, reliability is preserved in a long-run equilibrium sense of the word, meaning we meet all the reserve requirements. If new capacity needs to be built, it is built in the model, and the model chooses the least cost form of new capacity. But the model also considers whether it has existing capacity in place that is underutilized at the present moment and could serve those additional needs. So that's how we've done our analysis, and all I'll say is all this gets integrated. We find the equilibrium, we find the household impacts, and end up with our outputs, which are primary fuel market impacts, electricity detail on the electricity sector, and the general macroeconomic impacts. In order to do this, we have to take the compliance spending estimates that Mr. Bloomberg presented. We have to break it out by state, by the sector that bears the costs, broken out by these various sector levels that you see in the figure here, and by year. In other words, what's the timing? And as it came out in the earlier presentation, I'll just say right now, we assumed a timing where all of the states that face non-attainment under the new Ozone NAAQS will be basically on a schedule for marginal, as if they were going to attain on the date for marginal attainment. I mean, sorry, not marginal, moderate attainment, 2022. And so the spending has to occur before then. The only exceptions are California, which is well beyond 2035. I think it's 2038 when we get them into attainment, and the Utah, which I think we had as severe. So those have later timing, those two states, but everybody else is on this timeline. We essentially assume if there's spending in any of the states that are marginal, if they have to actually spend to get into attainment, we assume that they bump up and don't do that spending until they haven't sort of naturally come into attainment by 2020. Lost the date. Anyway, so basically we don't really have any costs for those that are marginal unless they really aren't projected to come into attainment by 2022. And then we assume they become moderate. This is just summarizing. Scott may not have even shown these figures, but this is just summarizing on the left which states are bearing those costs in our inputs, and the overall magnitude of those costs minus the electric sector retirement costs. And you can see on that varies over time, but on average it's running at about $100 billion a year if you just take a simple average. I have a point here. We do not include state SIP-related expenses. We do not include barriers to economic activity that may come from conformity planning or transportation limitations. We don't have any lifestyle alterations where the effect is directly on household sort of activity levels. but we just put in the emissions reduction costs and can go with it. And here are the results. Just a simple summary of them. At the national level, we see pretty large impacts that are on the order of 140 billion per year. And in Texas, and I put preliminary because these are kind of hot off the press and we haven't finished wrapping up the analysis, but these are the runs that we did. This is the run that we've done so far. Is $30 billion per year when stated annualized. On a present value basis, for the U.S. economy, it comes out to 1.7 trillion, and for the state economy, it's 0.4 trillion, or 360 billion. Now, here's where I can answer Roger McClellan's question of what is the gross state product of Texas, because this was something I had been looking up. That 30 billion is about a 1.8%. When stated on an annualized basis, about 1.8% of Texas's gross state product. And more specific to your question, right now, gross state product is 1.5 trillion. And I was remembering the wrong number when I came out with the wrong answer earlier. So it's pushing 1.5% to 2% for Texas. Now, for the rest of the economy, it's more like 0.7%. The bottom line there, you see, is consumption loss per household. This just takes, it's not GDP, it's the change in spending power, if you will, or the change in consumption that households bear. And it's for the average household. I should have stated that more clearly on the slide. Across the U.S., this policy, given the input assumptions on compliance costs that were presented earlier, is projected to cost about $830 per year for the average household across the U.S., but that's pushing up into nearly $2,000 per year for the average Texas household. Now, it shouldn't be too surprising that this is happening because, as you've seen, Texas is bearing in the cost estimates most of the costs. But again, the consumption loss per household is about 0.6% for the U.S.-wide, and it's about 1.4% for Texas's consumption levels. Again, these are pretty substantial. They are not out of line with what the empirical evidence was when you take into account that the empirical spending across the whole economy in Dr. Milovitz's historical numbers was estimated about 1.5% of the economy, and here we're looking at spending that's, well, for instance, from 1970 to 1995, the evidence is that spending for environmental regulations had been total $1 trillion. But as you may recall from the earlier presentation here, we're assuming U.S.-wide the present value spending is a total of $2 trillion. So this is this scenario is sort of doubling what had been the cumulative spending through 1995 for the historical studies. So it shouldn't be too surprising that the percentage impacts are projected to be larger than what we saw historically in that analysis, but they aren't out of line with what was seen historically. However, these are economy-wide and not sector-specific at this point. I'll show you some more details on that. People always want to know about impacts to workers. Because we don't have a transitional model, we're looking at a long-run model. The impacts to workers are, we don't get the transitional impacts. We don't get job loss. We don't get people being put out on the street because their factory that they were working at gets closed down. Rather, we just find really the productivity effect, if you will, which is the change in the real wage rate and the change in labor income that occurs once equilibrium is established and we're back to full employment. Again, these percentages aren't that different than what you were seeing from the prior slide. These are now stated in percentages. So it's on the range of 0.5% to 1% across the U.S., depending on the specific metric. And in Texas, though, the change in labor income turns out to be pushing up above 3%. Energy price impacts. So let's step back from things that people think of as macroeconomic level impacts, but things that are actually in some ways more real to the average person. And energy price impacts are fairly important in this rule, it turns out. What we see is at the national level, changes that are not insubstantial, particularly in gas prices and gasoline prices. Sort of for the delivered gas prices, depending on whether you're residential or an industrial customer, because they face different margins in the way these retail prices are calculated, can be 4 to 6%. In Texas, we're seeing the industrial delivered gas price rising as high as 8.7%. So it's pretty significant impact. But we actually see a much bigger effect in Texas on the prices of gasoline. This has to do with the refining activities. So where U.S.-wide we projected a 3.7% increase, for Texas we're projecting a 14% increase. And then electricity, the rates, again, nationally, they don't mean much since rates are highly localized electricity rates, but on a national average basis, rising by 2 to 3%. But in Texas, keeping in mind we closed down, actually this wasn't stated, yes, Mr. Bloomberg did state it, we closed down all the coal plants in East Texas, which is about, it was 90% of all of Texas's coal capacity, but it's about 20% of Texas's capacity in place today. As I said, all of that got replaced with the most cost-effective options available to Texas, which tend to not be imports because of Texas's particular electricity sector outline, but nevertheless, there's a lot of opportunity to use existing capacity in Texas as well as build more. Anyway, the rates are going up. The industrial rate calculation is up to an 8% increase. These are averages, by the way, across the entire time period that we analyzed from 2017 to 2040. They do vary from year to year, but rather than show you too many graphs, we thought we would summarize things as average changes. The Henry Hub, by the way, for those of you who don't know natural gas markets, that's sort of an indicator of market prices that are from which gas prices across the entire U.S. are sort of keyed off of with sort of regional adders. So it's sort of an indicator, a commonly used indicator variable. That's why we don't have one for Texas. It's just sort of a national estimate. And then delivered prices just have, sort of the regional uptick as well as the distributional the additional margins that go with each region. I don't have coal in here, but we'll see coal in a second. But I'm first going to turn to state-by-state impacts. So I'm not going to make you read this chart. I'm just going to show you that we have the numbers. Instead, I'm going to graph these. For every state, we have a cost per household estimate for the individual states. This is from the work that we did for the National Association of Manufacturers. And each state also has a percent reduction in its emissions that it needs to achieve. So I've graphed the percent reduction in emissions. These are the percent reductions that EPA says the states need to achieve in their existing emissions. So on the, and then I've graphed the cost per household that was estimated from our analysis on the vertical axis. And the dots just refer to different types of states. The color of the dots, that is. But the main thing to note is there are states that have no control requirements. Those were the ones that were not colored on that map that I showed earlier. Those are states that are projected to be in attainment, as well as our EPA did not assign them any emissions reduction costs to help some other state get into attainment. And you can see they bear a cost. It's not as high as the costs of the states that are bearing costs, but they are not sort of getting a free ride, and they're not actually benefiting in a sort of an aggregate way from the misfortune of the other states that are bearing these costs. For the most part, the purple ones, they run in the range of $250 to $300 per household average. But you see a few of them that rise above that are the little green triangles. Those are states that have a lot of coal output, and their economies depend on continuing to sell coal. And so you see that a couple of them that are coal-intensive states but have no compliance costs actually rise up into the range that's not inconsistent with the level of many of the states that are bearing fairly substantial reduction costs. Why? Because those other states, which are the red dots over to the right, are using less coal as part of their compliance. So next thing you know, the effects are being trickled back to the coal-producing states who might otherwise think they're off the hook. And that very high-cost state, the Green Diamond at around $4,500, that's Wyoming. It does have some estimated reductions, but its economy is very, very dependent on coal and oil refining as well. Oil and refining, that is. And so it really takes a huge hit, even though it's actually only got about a 20% reduction requirement. That is the way I was saying at the start, that a model like this helps you understand who bears the burden, and that the burden may not actually be where you see the costs, the compliance costs being targeted. Now, on this chart, there's a lot of scatter. You can see this. It's not an obvious relationship. Again, this is because each of these states has a very different economy, and the different sectors are bearing different amounts of costs, as well as they're bearing different kinds of demand effects when other states don't want to consume as much of their input. So there's a lot of scatter, and that's why you need a model like this, because there's just no way you can come up with a simple relationship and say, well, for every dollar you spend, you'll lose 1% of some output measure. The blue star is Texas, and I just highlighted it since I've been highlighting their results throughout. Here I have Texas having a 62% reduction, but in fact it's about a 72% reduction, I think, for East Texas, and then a much lower percent reduction in the West, although we did put some costs into the West simply because EPA did, not because we could see a real reason for it, but we couldn't come up with a reason to undo them and move them. Besides, we also couldn't, if we took all those additional controls that are in West Texas and said, well, these really have to occur more in the East, because that's where the non-attainment is, we would be seeing 90+% reduction in the East, while West Texas would be doing nothing. So it was just, we knew what that would do to the cost estimates, and they're already high enough, as you know. So we just decided to let those be where they are. Okay, so this gives you some sense of distributional impact, but what's interesting here is very few states, no states get off the hook entirely, and a lot of the price effects that you are seeing here are mediated through energy markets, along with the direct cost to the sectors that are in the states and have to reduce their tons. Sectoral impacts then. As I said, a lot of the variability in those, in that scatter chart you saw on the previous slide is because of different makeup of the sectors in each state. And really, this policy is not about manufacturing. There are costs, a lot of costs that are going into the manufacturing sector, and there are a lot of costs that are going into the electricity sector, but there are going to be needs to reduce emissions across many sectors of the economy, and so you actually don't see much focal point of the impact on output in any particular sector other than coal. And we've talked about the reason for coal. That's just the electricity sector having to shift out of coal in order to get cost-effective reductions. And I should be clear, the reason we are closing down coal plants in our assumptions is because it turns out to be the most cost-effective on a dollar per ton basis thing that we could find, short of maybe the very, very oldest of the vehicle fleet turning over, quote, early. So some of those are very cheap, but there are not very many of them in tons. When we looked at the sources that remained and we looked at the options, reducing NOx by closing down coal-fired power plants and replacing them with gas-fired or whatever else would be the mixture, was very cost-effective. So this is a way that we kept our costs from just blowing out of control. It was a fairly substantial chunk of the marginal cost curves extent, x-axis extent, before we started having to go into the extrapolation based on things like vehicle scrappage. So it hits one sector very large. It also affects electricity prices, but it is a very cost-effective measure, and it's hard to believe that when states have to cut their emissions, their NOx emissions to the bone, if they've got a coal-fired power plant still generating, that they wouldn't look to that. And in fact, it's more cost-effective, we find, to close them completely and replace them than to put a retrofit of an SCR on them and get, if they don't already have that SCR. But many of them have the SCRs already, not all of them. Now you see natural gas increasing, and that's to be expected because we're switching from coal into gas. So the output of the gas sector goes up, and that's the one sort of sector, these are aggregate sectors here. That's the one sector at this kind of level of aggregation where you see benefits to the sector. And I will tell you that natural gas increase helps Texas. But Texas, you saw that this is in that benefit to gas is in that aggregate Texas result that I showed you. Now, business profitability is a very different thing than changes in output. Output is just the value, the dollar value of what is made and sold by the sectors. It's sort of a measure. It's just basically the value of the output. It's dependent on the price of the good. If the price goes up, that'll actually drive output up as well. Business profitability is a really different measure, and we haven't done it. It takes a really different kind of model to do because you need facility-specific information, but you need to know how much of the cost is an individual business able to pass through and what are their current profit margins, et cetera. So there were some empirical studies that looked at, mentioned I think sort of like an 8 or 9% effect on manufacturing profitability. We just don't have any kind of measure at all. These numbers can't be compared to that one. Now, economic impacts are widely expected from any of these kinds of regulations to be distributed regressively, meaning the lower income households are expected to bear more of the burden. A larger proportion of their available income, their disposable income, is likely to be absorbed by the cost increases in goods and services from regulations. That's just a very common finding, and in good part, it's because things like energy and commodities, goods and services are a larger proportion of the spending of a lower income household. They just have to spend a bigger fraction, for instance, of their income on energy, keeping the house warm, that sort of thing. So when energy prices go up, they have little route to escape, and they end up just bearing a larger cost relative to the higher income households, who may consume a lot more energy, but it's maybe a smaller part of their household budget. Now, we could not analyze this with the tool that we used for this analysis. We do not have income groups in our tool. It would be a nice extension of our model to be able to have more than just an average household in each region, but we've never actually been able to find the wherewithal to invest to make that adjustment. Other models can do this, and when I say it's expected that the results it's commonly found that the results are regressive. That comes from other models that do have that detail of income levels, income groups in them. But there are reasons to expect that that would be true. So I'm really, at this point, not talking about our results, but just talking about thinking about economic impacts generally. As I said, energy costs do tend to be a larger fraction of lower income households, and that's one of the main reasons to expect it. But another thing you might think of is we have a fair amount of scrappage of older vehicles going on in our cost estimates, at least for the states that have really strict deep cuts that they have to face. And some of those are, vehicles, some of those are trucks, but to the extent these are vehicles, scrappage doesn't mean making these vehicles available to the lower income households to buy more cheaply. They get taken off the road. Suddenly cars are more expensive across the board for everybody. It'll probably be the higher income people who take the subsidy and buy the newer car that'll be far lower NOx emitting, maybe even lower CO2 emitting, but I want to point out we're talking about NOx here and not CO2. That just basically takes away a low-cost transportation option, or at least personal transport, well, household, whatever, a vehicle, personal ownership of transportation, that's going to place a greater burden on the lower income who have no choice in the matter. They're not the ones voluntarily scrapping the cars necessarily. Anyway, there's a lot of interesting stories around vehicle scrappage programs and where the cars come from that I'm not going to go into. I just wanted to make the point here. And I think a lot more analysis is needed on this point. This may be one of the most important aspects of the potential economic impacts of a standard like the Ozone NAAQS standard, which is going to hit across so many sectors and into many of the smaller sources of emissions across the economy. It would be nice to see some more economic impact analyses that have got that feature in them. And I'd like to get close to wrapping up here. What time am I supposed to end? Okay, that's what I thought. I wanted to make sure yeah, I'm getting close to questions here. Okay, so let's acknowledge the limitations and the uncertainties here. We know the compliance cost inputs are highly uncertain, and of course the economic impacts are just driven by those. Input, you put the cost up, so too will the economic impacts go up. The only thing we're really learning about this is where do they then reside in the economy, what's the incidence of the impacts, and that may differ as you change the compliance cost inputs in a way that's not proportional with just how much lower the total cost inputs were. That's where you might see sector-specific differences and regional differences as a result of changing our cost assumptions. But we need to recognize it's a wide range. We've looked at the cost estimate that on a present value basis is $2 trillion. EPA has said it's 0.2 trillion. They haven't said it in their RIA, but we've calculated an equivalent present value from their RIA's costs, and it's about 1/10 or 0.2 trillion. 200 billion per year. This is such a wide range. You could scale these impacts up and down, but you can't scale the distributional impacts up and down to understand the differences. Also, we have assumed, and this came up in the questioning before, that the compliance spending will occur on schedule, on compliance schedule, which means all of that spending, except for California's and Utah's, is occurring by 2022, at least the capital spending phase. There's O&M that then kicks in afterwards that goes on permanently, really. That if we could costlessly push off the timing, the impacts would certainly become less. If for no other reason than the miracle of present value, but also because there are trends in the baseline where you're not trying to where certain control measures will occur anyway that don't have time to occur by 2022 or earlier. We haven't included regulatory pressures, whether the regulatory pressures would spur innovation. This is the Porter hypothesis, for instance. The empirical evidence for this is that to the extent it happens, I would describe it as it may happen in niches, not necessarily on a widespread basis. So we don't have a reason to believe that we would have net positive economic outcomes as a result of such innovations and this kind of spending. But nevertheless, we don't have those innovations endogenously in our model in any way. We have assumed that all the costs do get passed through into product prices. And the importance of this is that even if this has to do with the distributional effects more than the net aggregate effects. But so our distributional impacts are just assuming cost pass through, and then everything comes back to the consumer, the household, depending on what they're consuming. We haven't included transitional effects. I mentioned that at the start. Those would drive up the costs, particularly in the near term, the first 5 to 10 years of the policy. But we've just assumed that there are really no displaced workers in a sense. We do see labor reduction in job equivalents, but it's more associated with equilibrium reductions in wage rates. due to reduced productivity. And we haven't included, to go back to Andrew Huxma's comment, we have not included the effects of constraints on development projects in regions that are in non-attainment, nor local government spending costs. We haven't done anything to change tax rates in order to fund subsidy programs, for instance, which would have a whole kind of effect of their own that we just simply didn't analyze. This is my diagram showing all the things that we didn't include, depending on the severity level of your non-attainment. But keep in mind, these would apply just to the areas that would be designated as non-attainment, although quite a few areas will be designated as non-attainment, say in 2017, when designations will be due. Even if in a baseline and they sit still, by 2025 they would be back into attainment with doing nothing. They will nevertheless be in non-attainment and face these kinds of pressures, which will be constraints on development and development-related activities for those areas. And those are not in our analysis. So just to wrap up then, we are seeing larger than historically experienced costs in at least even, I would say, even with using the EPA's lower cost estimates. And the impacts are projected for all states, including states with no compliance costs. They are facing net macro impacts due to the economy-wide impacts of a policy, and that's why you need an economic impact economy-wide model to look at that. And we are finding that many of these impacts are filtering through, sort of, if you will, on the coattails of energy price effects due to the compliance actions. We see natural gas as a sector that stands to gain, at least in terms of output. But there are a number of additional issues around that that I haven't analyzed or talked about that might make that less obviously a gain in the long run. And the regressivity of impacts stands as an important type of household impact yet to be explored. Thank you.
Ann, thank you for that window into the black box for a simple lawyer. It was very useful. That's quite a model that's been constructed. Talk a little bit more about the transitional costs and what that might do. So I understand it. Is it labor and capital moving in some costless way to the new equilibrium that you have in mind? And and how might it affect different sectors? You know, I just trying to understand that. That was on your third to last slide, I believe, where you emphasized transitional costs were not.
The main place people are concerned about transitional costs is usually around workers, because if certain kinds of manufacturing goes out of business, like a coal plant closes, will that worker find a job at the next coal plant? Well, it won't be a coal plant. Will they find a job at another in that industry?
Yeah.
Many workers who get displaced find they have skills and capabilities that really aren't where the new jobs are, and so you end up with this bubble of people going on to the, out looking for work as the transition starts to happen, and having difficulty making the transition just due to a mismatch of skills with and location too, and so sometimes that can last quite a few years, and Professor Miliband mentioned the evidence is that it's the older workers that some of this impact can really become a fairly big cut in their incomes, and they might endure these impacts, for 5 or 10 years after they lost the job. And our model just doesn't assume it. Now, there are also issues of capital transition and all, which actually, for instance, in our, we've got that bottom-up aspect in our electricity sector, which is intended, it was built in there to be able to capture transitional issues, like how fast can you change over the technology in the electric sector, which is one of the big sectors that needs to address change. So we actually built that in specifically to capture what we call transitional effects, at least with respect to the technologies and the availability of the technologies. But then across the rest of the economy, we've just assumed, if capital is perfectly mobile, that there's an investment in capital, and that takes away from investing that capital elsewhere. It becomes unproductive capital. and so it doesn't contribute to the continued growth of the economy. It doesn't, we don't have like a heightened cost associated with scrapping the old vehicles. We just say there's a loss associated with throwing out good capital when we scrap vehicles. So mainly it's the worker part. I think that's the most important element that's missing.
Great, that's helpful. Just two other aspects. One is a lot of utilities are investing in, for mats and for compliance, and I'm just wondering if in your analysis with those recent large investments or soon-to-be large investments, whether that would still be the least cost way to proceed, turning those off. And then second, I found the whole discussion on the scrappage very interesting, but I think there'd be a lot of local pressure perhaps about those programs, and if those programs didn't go forward, how would that might affect costs? I mean, how much higher could we see things go if the scrappage didn't take place? Because that is a very kind of touchy area, I think.
Okay, well, the MATS rule is in our baseline, so there are a lot of retirements occurring before we get to 2017 that are just not part of our costs. They're happening for free, if you will, in our analysis. And so it is a big transition for the utility sector. There's quite a lot of retirements that do end up happening in this time frame. There's a question of how feasible is that. We haven't said you can't make this much turnover this fast. So maybe that's part of the transitional cost. Maybe we can't turn over that much capital that fast in the electric sector, but we haven't assumed that we can't. And additionally, so they remain, the ones we retired, they are cost effective to retire because our projection under the MATS rule is they would continue to be operating under the baseline. The scrappage, we've assumed a cost, an incentive to get people to voluntarily scrap their cars, and the size of that subsidy has to, of course, go up if you want to get more and more. It depends how many cars you really need, or vehicles you need to pull out of the system in your state. I guess I can't address this question of pushback. It certainly becomes costly, but obviously Texas has already been doing programs like that. We know California has done it. The U.S. has done it. So I don't know that I've heard of pushback on that, but maybe the state can speak to that.
I think you've given us a very good example of a general equilibrium analysis of the cost potentially associated with meeting the 0.65 parts per million standard. I just want to say that a thorough general equilibrium analysis, which I hope one day we'll be able to do, would also incorporate the beneficial effects. And so if improvements in air quality, in ozone levels, made people much healthier, as some of the optimistic studies suggest, then they would be more productive at work, and those would be mediated through the economic model. Higher productivity means people will be paid more, they'll buy more things, and that will be good for other sectors, et cetera. I think we also need to point out that you're looking only at those things that turn up in GDP accounts, in market activity. It could be that the economic impacts are exactly as you've projected them. Suppose one of the benefits of a tighter ozone standard, and I'm not saying this is the case, so this is a hypothetical. Suppose kids are much healthier and they're able to play outdoors much more longer and they don't sit on their rear ends and play video games. That may not be manifested in market activity, but we might all think that that's a wonderful thing. Improvements in visibility are a great thing, but that doesn't necessarily turn up in economic activity. So a true general equilibrium analysis would try to push through both the costs and the beneficial effects to the extent they manifest themselves in economic activity.
Okay, well, I would agree that if they manifest themselves as productive activity as opposed to willingness to pay, that to the extent that there's strong evidence that there would be these benefits in a productive sense, that's reasonable to include in an analysis. We've been through a day of listening to the evidence on whether there's any kind of any kind of real health morbidity effect that really is affecting, productive workers. And I'm just saying if it were true, then I would not disagree with that. But I disagree personally with the idea of taking an economic impact analysis to the point where you're trying to replace a benefit cost analysis with it. And you were referring to visibility benefits and children at play and all of that. And I think that those are better left in a different world as a benefit. I mean, we're not here to do a benefit cost analysis. We're not even supposed to be talking about costs. But so the main point here was to provide context about the socioeconomic impacts. But if we were in a world where benefit cost analysis could be done, then those would be appropriate to incorporate there, I would say.
Don Arbo will get special dispensation for the quickest question ever.
Okay. Well, thank you all for gathering here today, and as I continue my remarks here, I'd like to ask the following question. So, do you know if there have been any non-governmental ex post analyses of the costs of a previous, like a NOAQS or Ozone NAAQS to non-governmental ex ante costs? And if so, did you use them to help build your blue model?
I'm sorry, Don, I didn't quite get the question.
Was that not loud enough?
I'm sorry, I just kind of lost the, you're saying, has anybody done an ex ante NOAQS analysis, NOAQS impact analysis before?
Ex ante and, ex post, and
ex post.
compared it
To an
to
ex
its
ante.
own ex ante.
Okay, more retrospective analysis. Okay, specifically on the NOAQS or NAAQS? Okay, I'm not aware of one specifically around a NAAQS. The one I'm aware, the ones I'm aware of have been related to the cap and trade program, Title IV cap and trade program for SO2 for utilities. And so that has come in cheaper, but that was actually a market-based measure, market-based approach, which is a lot different than what we're looking at with SIPs. So I don't know that we can extrapolate from that readily. There have been some other retrospective looks, but I don't know of them for NAAQS.